equal to 0 and all fg homogeneous of the same degree, right? And then I divide this by f over g, twiddles f primed over g primed, if and only if you know what. I want to say g not 0. If and only if fg prime. Right? I get a field. Right? Called the rational function field. Of P1, P1K. Okay, so this word, this rational function, so I come back to this meromorphic function I had written up again. I've noticed Japanese mathematicians speaking English distinguish very carefully between meromorphic functions in complex analysis and rational functions in algebraic geometry. And they do this despite the fact that in their own language they only have one word for it, which is this thing I wrote out before. So rational function, this means partly defined, partially defined. Later on we'll have a topology, and where the place where they're defined will be dense open sets. At the moment I'm just working with this much simpler setup, partially defined functions everywhere, locally, the quotient of two polynomials. Okay, so now I can go back to this. Now I can go back to this setup and try and understand what does it mean for these two varieties to be isomorphic. So I wrote down this expression here, and I wrote down a much longer expression here. Right, which are basically the same thing. So I want to call this SD of UV to be equal to that expression over there. So it's U to the D minus 1V, and so on, V to the D. So this is just a set of monomials. Right, so why do I call it S to the power of D? Well, there are some places in algebra where, given a vector space, you can choose a basis of it or not choose a basis if you like. Here I'm saying UV is a two-dimensional vector. UV are functions on a two-dimensional vector space, and I've chosen a basis. Right, but if V is a vector space, I can take S2 of V, symmetric tensor product, and so on. So I can take SD of V, symmetric D tensor product, and then these guys, these vector spaces can be defined intrinsically without saying basis. Right, but at the moment I'm just doing I'm only writing this down here to explain why I use the notation S to the D. S to the D means symmetric tensors in U and V. So I've got this is a vector space of dimension D plus 1. Right? So I have something here of these guys here of degree D, These are the monomials of degree d in U and V, and if you count how many of them there are, you get d plus 1. Right, just counting along there. Right, and this is what I've used to do this map this way. In the case d equals 2. So let me explain now how to construct the inverse of this map. So it's convenient to have some notation. Let me call this I, and let me call this pi. So how are we going to get this pi? Well, what do we want it to do? We want it to be the inverse of I. So this means, for example, if I've got x and y, then just knowing x and y only, if I know x and y, then, basically I should know the ratio u to v. So I could take the inverse map here as just being, well, let's take this triple of points here, x, y, z, satisfying x to y to z, satisfying this equation. Let's take this triple of points and let's just map them back to, so let's do x, y, z, so, sorry, x to y to z. These are ratios, these are points of P2. Let's map this back to, I want something u to v which sort of matches up with this, so let's just map it to x to y. Okay, then I'm mapping forwards by this pair uv goes to u squared uv, v squared. I'm mapping back by this triple u squared uv, v squared, satisfying this equation goes back to the ratio x to y. And so, u squared to uv, so thinks u squared to uv is much the same as u to v. So in English grammar, this means he thinks, or he or she thinks, to be politically correct. Okay, so you see what I've done. I've told you how to construct the inverse map. On the other hand, there is a kind of little problem with what I've said. So can you see what the problem is? So there's a point on this curve which I already mentioned, the point 0, 0, 1. Right? So he's a perfectly good point of this. And he is the image of a point here. On the other hand, if I try to define the map back by this expression, I'm sending 0, 0, 1 into 0, 0. And 0, 0 doesn't make sense. 0, 0 is not a well-defined ratio. It's not a point of P1K. Right? So what should I be doing? What's the way around it? Well, if u is 0, I'm at the point 0, 0, 1, then how else? Is there a different way of obtaining this ratio u to v? Huh? What should I do? Obviously, I can just say, if I want to, I can just say, set theoretically, I'm going to take the point 0, 0, 1 and map him back to 0, 1. But the problem, that's only defining it at a point. It's not defining it in a neighbourhood of the point. I want it to be defined in a neighbourhood of the point. Anybody see what I should do? So pi. So the solution is define pi by x, y, z maps to x to y, sorry, this is ratio, x to y to z, x to y, if x is not equal to 0, and maps to y to z if z is not equal to 0. Right? What happens if they're both not equal to 0? Well, if they're both not equal to 0, then this ratio and this ratio are the same. We're saying that x over y equals y over z, and that's when both of these are ratios of non-zero numbers. This is just saying that x, z equals y squared, and we know this is true. Okay, so look, this the first step I said here is plausible. It's something that looks right. It looks that I'm doing a map back the other way. I'm doing a map from C back to the curve P1, and it's obviously sending points with the ratio u to v with u non-zero back into the points u to v, just by taking only the first two coordinates. Right? And that works perfectly well as long as we're not at this unfortunate point 0, 0, 1. Right? So if we are at the point 0, 0, 1, then this ratio is certainly well defined. Right? And furthermore, the two expressions agree whenever they can. Whenever both of these guys are defined, then the two ratios agree. Moreover, this covers the whole plane, because if x is 0, then y is 0. If z is 0, then y is 0. So if x and z were both equal to 0, then y would have to be 0, and that's a contradiction. So here, x, y, z is not equal to 0, 0, 0. So 1 of x, z is not equal to 0. Okay, so this is a simple argument. It's a very simple argument. The only point is to understand that it really works everywhere. That it works at every point of the curve C. So this is the little argument here. At every point of the curve C, either x is not 0 or z is not 0. Right? Remember the picture. I can't remember what the names of the coordinates were, but here is the picture of C. Right? It's a parabola viewed here, and it's a parabola viewed there, and it doesn't pass through that point. Okay, so I'm telling you that this is an isomorphism. I'm telling you it's a regular map in one direction, and it's a regular map defined in the other direction. And I haven't explained what morphism is, and I haven't explained what regular is. You just have to take me on trust that when these things do turn up later in the lecture course, that this will be a particular case of it. Right. So whilst we're about it, let me explain another little point. That I've been talking about taking P1 here and mapping it into P2. So we're over a field K. I have in mind mostly that K is C. Mostly. Or any field. Right. So I did this with by doing u squared uv v squared. But I could equally well do it for different values of d. And this is interesting in various different ways. So here's P1. Here's P1K. Let me map it into, let me give a famous example. P3K, mapping UV into U cubed, U squared V, V squared, UV squared, and V cubed. Okay, so I'm going to call these guys X, Y, Z, P. So, we're going to understand that the image variety, that the image is still defined by a set of equations. So here we map the UV forwards like this, and lo and behold, we discovered this thing, X. We discovered that this times this is this one squared. So can we see some equations? So let me write C in there for the image. So can anybody guess some equations that vanish on C? So suppose, the person who says an equation, a true equation, gets a free beer.
We need two equations that
No, you've seen it before, it's not fair. Yeah, what you said is completely right. Anybody else? Come on, it's not very difficult. For example, what do you get if you multiply X and Z? U to the 4 V squared. Okay, can we get that in some other way? Y? Y squared. Yes? So some other equations. So that's sort of basically the same as here. These are 3 consecutive powers. If I took 3 consecutive guys here, I took the product of the 2 outside ones is the middle one squared. Right, so can we do it again? Xt equals yz. Okay? So, I suspect that some of you have actually know the answer and are too shy to shout it out. If you were all completely in the dark, I would say, well, look, chaps. I've got the curve. This is supposed to be a curve in 3 space. So this one is dimension 3. We don't really know what dimension is, but we can sort of guess. This one's 3-dimensional. This one's 1-dimensional. We've written down 2 equations, so that should be enough. Okay. So what's wrong with that? Well, one thing is wrong, that is that you can probably guess a 3rd equation if you think about it. But what else is wrong? So suppose take these 2 equations. Is it true that these 2 equations define C? those two equations certainly are zero on C. They're certainly true on C. But do they define C? Is C the whole locus given by those two equals 0? So look, I do hundreds of these calculations like this all the time. Now I do them by computer, and you can do 1,000,000 in a second. Right? And there is something here which is entirely right, which is, say, we've written down those equations, and if we are allowed to take rational combinations, in other words, if we are allowed to divide those equations by each other, and so on, we would get everything we want. Right, so let's just write down x, z equals y squared, and xt equals yz. Can anybody, if I gave you those two equations and I said you get a candy bar if you tell me some solutions to it, what are the solutions you can see? Or, the other way around, what happens if I beat you over the head if you don't tell me a solution? Tell me some solutions of this equation, of those two equations. Sorry? 0, 0, 1, 1, or 0, 0, AB. So the point is, you look at these two equations, and probably we've done enough work, haven't we? We've got a curve in 3 space. We've got a one-dimensional thing in 3 dimensions. We've written down 2 equations. Surely that should be enough, right? And the answer is no, because x equals y equals 0 is a line in P3. Right, here's my P3, here's the curve I'm interested in, and here's some other line. Right? And this line here, 0, 0, AB, is not in the image here. It's certainly not in the image there. Because if x is 0, then u is 0, and that means z is 0. Okay? So what's the remaining equation? I better have some equation that doesn't have too many x's and y's in it. Sorry? So, you take 2 guys there, then it's this one squared. Take 2 guys there. What's the equation I'm referring to? You have to speak louder. Yeah. Okay. So you said earlier you'd of course seen this problem before. So. So I want to just try to get a little bit of not just calculation but understanding of what these equations mean. So, suppose I ask you, suppose I take, for example, u equals 1, right? Then I'm telling you 1 v squared v cubed, right? And then I ask you, what's the image? It's a set of points x, y, z, t with x equals 1, and how do you describe it? How do you describe it in words? As writing a prose essay. look, I mean, what's the next term in that sequence? What do you think? What do you think when you see that sequence? You know, think it's a geometric progression. Yes? And, you know, this is exactly what we're doing. We're just writing down a geometric progression. A geometric progression with what ratio? So u cubed, u squared v, uv squared, v cubed is a geometric progression with ratio. Right, so geometric progression is something like a, ab squared, ab cubed, ab to the fourth, and so on. Right? And this b is the common ratio. So what's the common ratio here? So with common ratio u to v. Yeah? And so here where, you know, we don't understand anything, so we start calculating, and we say, aha, yes, I notice that equation. All right? But here we're doing something more sensible. We're saying, look, these expressions here I'm writing down, u cubed, u squared v, uv squared v cubed, they're not just any old things I'm writing down, they're formed by a certain rule, and we're trying to understand what the rule is. And the rule is that this is a geometric progression with this common ratio. So if you think about this, so, you know, so there's often a quick way of going somewhere, and you can go somewhere quickly. You know, you can, if you have to go from here to Jeju Island, you can take the plane, or you can take a bus and then take a ferry boat. If you take the bus and take the ferry boat, you see much more of the country. Right? If I tell you just the answer, then you're missing all the countryside. You're missing all the thoughts. So look, this is. If you're going to do research in algebraic geometry, you're going to see equations like this a million times, right? So what is it? What are the properties that what are the properties of these numbers that make it into a geometric progression? Geometric progression is something where there's a common ratio between the terms. Yeah? So there's a really quick way of writing this, which is to write x, y, y, z, z, t. Think of this as a matrix, right? And what are those equations telling us about this matrix? Has what property? Rank 1. So rank 1 means, you can say rank 1 in two different ways. It means all 2 by 2 minors vanish. Yes? So then you get xz equals y squared, and xt equals yz, and yt equals z squared. Or you can say it another way. You can say it means that this row is proportional to that row. In other words, the ratio u to v is defined. The ratio. Yes? And so, you know, you can see. So now how do we, if I ask you now how to form the inverse here, how am I going to form the inverse? So you know, it's a proposition. C in P3 is the equation, is the locus defined by the equations rank of x, y, y, z, z, t less than or equal to 1. Right? So actually equal to 1, but if I write less than or equal to 1, then I'm writing down polynomial equations. To say that a matrix has rank less than something means all the 2 by 2 minors vanish. Right? So every time I calculate a 2 by 2 minor, it vanishes. Right? And so, what do we have to prove? What do we have to prove? So here, when I was doing this guy, what I had to prove, exactly what I had to prove, the curve does not pass through that point. At every point, either x or z is non-zero. Right? So I say in this, so notice this matrix isn't any old matrix, so these coincidences. Right? So at every point of the, so take the locus in P3 defined by these equations. I say that at every point either x is non-zero or t is non-zero. Because wherever x is 0, also y is 0, and then also z is 0. Right? And wherever t is 0, then also z and y is 0. So that's exactly like this picture. Right? It meets the x-axis, it meets x equals 0 at a place where also y is equal to 0. Right? So consider the locus defined by these equations. At every point, either x is not 0 or t is not 0. Right, so if x is not 0, then this ratio x to y already tells us everything that we need to know. Right, if I know x to y, then I know y to z, and I know z to t, so I can fill up the whole matrix any old how. So if x is not equal to 0, I can set x equal to 1, then y tells me everything. So I had step 1. This is step 2. So the locus rank of that lies less than or equal to 1 has x or t is not 0. Right, step 2. If x is not, well, I can set x equals 1, then y tells me everything, because then it's 1, y, y. The guy I've got to put here to make this 2 by 2 minor, there's no choice, it's y squared. And then I've got to put y squared there. I have these coincidences. And then there's no choice here, it's got to be y cubed. Right? And so this is exactly the argument I used here. This is exactly the same argument. I told you this x over y is y over x. So that's a 2 by 2 minor. That's a 2 by 2 matrix, and I'm saying its determinant is 0. So here I've just got a slightly longer matrix. And I'm saying not one minor is 0, but all 3 minors are 0. Okay. So anyway, so look, I said I don't want in lectures just to repeat the material that's in the book. It's boring for me and it's boring for you, right? So, but I do ask you to read the book. So the chapter 1 of the book, has another, a number of quite fun, jokes about algebraic geometry that everybody should know, and it should. So some of you, I appreciate, some of you are advanced students and already know a lot more. For you, it will take about 1 evening to read the chapter. So maybe an hour. For those of you who don't know the material, then, you know, if you're going to study algebraic geometry, you should know this stuff. It's about the easiest material you'll ever find in algebraic geometry. And the exercise at the end of the chapter, well, you know, you can only learn, you know, I stand at the blackboard and I harangue you about these. I try to force you to be interested in these calculations, but that's not how mathematics works. I mean, if you understand mathematics, you do the calculations yourself. You have to do the calculations yourself to, you know, it's like, exactly like, you know, the kid riding the bicycle. No amount of lecturing is going to tell the kid how to ride the bicycle. It has to be, you know, he has to get on, he has to ride around, he has to fall off a couple of times. Okay, so I'm going to leave it for this week. I'll probably say a little bit more about the material of chapter 1 in the first lecture next time, but then I want to go on to the next chapter, cubic curves. Again, I won't lecture the material in the book, but I will talk around it. Okay, so if you have problems, come and talk to me now, or as I said, talk to me later or send me an email.